Hello guys! For this afternoon, I am going to discuss the topic all about groundwater and seepage according to variability. First up, for the introduction, in no field of engineering are practitioners faced with more complex and uncertain sets of conditions than those concerned with groundwater systems. Unlike their colleagues in other engineering disciplines, who have the advantage of observing the performance of many prototypes under relatively known states of input, groundwater engineers generally deal with systems that are custom-built and tailored to special demands and specific locations. Add to this the very size of projects and the expense of underground sampling and data acquisition. So for this chapter was written with the following main objectives. So the objectives are as follows. First, to provide with an organized, logical, and systematic body of knowledge for the solution of groundwater and seepage problems. So later on, we will discuss the principles as well as the solutions on how to solve specific problems concerning with the groundwater and seepage problems respectively. Then the next main objective is to provide with probabilistic concepts and techniques to account for uncertainty in designs and to illustrate the relevance with application to practical problem situations. I am also going to discuss some of the groundwater fundamentals, and the first fundamental that I'm going to elaborate and to discuss is all about the Bernoulli's equation. So the Bernoulli's equation is somewhat very common, or I think some of our classmates and colleagues here in MAP 313 have already familiarized this particular topic or principle way back in the college years, more particularly in the subjects fluid mechanics and hydraulics. So for the Bernoulli's equation, underlying the analytical approach to groundwater flow is the representation of the actual physical system by a tractable mathematical model. In spite of their inherent shortcomings, many such analytical models have demonstrated considerable success in simulating the action of their prototypes, as is well known from fluid mechanics for steady flow of non-viscous incompressible fluids, or the Bernoulli's equation. Just as a sort of reminder and a review, so Bernoulli's equation principles, it states that the energy per unit volume before is equal to the energy per unit volume after, and it is given with the following equation: P sub 1 plus 1/2 rho V sub 1 squared plus rho GH sub 1 is equal to P sub 2 plus 1/2 of rho V sub 2 squared plus rho GH sub 2, where P refers to the pressure energy, the 1/2 rho V sub 1 squared refers to the kinetic energy per unit volume, and the rho GH sub 1 refers to the potential energy per unit volume. Another groundwater fundamental is what the so-called the Diracs Law. So under this law, or under this principle, the flow of groundwater is taken to be governed by Diracs Law, which states that the velocity of the flow is directly proportional to the hydraulic gradient. A similar statement in an electrical system is Ohm's law, and in a thermal system is the Fourier's law. So the grandfather of all such relations is Newton's law of motion. In the Diracs law, we assume that the flow is laminar and the soil properties do not change with time. And the Diracs law is given with the following equation: Q is equal to KIA, where K is the hydraulic conductivity or permeability in terms of centimeter per second, and I is the hydraulic gradient, and A is a cross-sectional area of the flow. And other groundwater fundamentals that should be taken into account is the so-called Reynolds number. There remains now the question of determination of the extent to which Diracs law is valid in actual flow systems through soils. Such a criterion is furnished by the Reynolds number R, a pure number relating inertial to viscous force, which is defined as follows: R is equal to VD rho over mu, where V is the discharge velocity in terms of centimeter per second, D is the average of diameter of particles in terms of centimeter, rho is the density of fluid, in terms of grams per cubic centimeters, and mu is the coefficient of viscosity in terms of gram second per centimeter squared. Another groundwater fundamental is the homogeneity and isotropy. If the coefficient of permeability is independent of the direction of the velocity, the medium is said to be isotropic. Moreover, if the same value of the coefficient of permeability holds at all points within the region of flow, the medium is said to be homogeneous and isotropic. If the coefficient of permeability is dependent on the direction of the velocity, and if this directional dependence is the same at all points of the flow region, the medium is said to be homogeneous and anisotropic or allotropic. To understand and elaborate more about the topic groundwater and seepage, let us relate these particular topics in our field of specialization, which is the civil engineering works. So we all know that groundwater is a natural phenomena that is present in a natural or undisturbed soil properties. And it is very important that we shall consider the effects of groundwater in all the designed, in all the constructed infrastructure projects in order for us to have a sustainable infrastructure projects. For example, to have a sustainable vertical structures, to have a sustainable horizontal structures, or those roadway structures. So, groundwater and its effects on infrastructure projects, the impact of groundwater on the construction, maintenance, and long-term performance of highways and highway structures must be considered on every project. Excessive and uncontrolled subsurface water has been responsible for large numbers of pavement and slope failures and unsatisfactory projects. Subsurface drainage is essential for economical, long-term performance of roads and highways. This chapter discusses the effects of groundwater on highway projects, identification of groundwater problems, and methods for control of subsurface and subpavement water. Procedures and criteria for subsurface drainage design are presented, with emphasis on a multidisciplinary approach to groundwater problems with interaction between the hydraulics, geotechnical, and roadway engineers. So, it is very important that the groundwater or the subsurface or even the subgrade water must be investigated prior to the construction of that particular structure, because this particular scenario may affect the quality of materials, such as the quality of our concrete, and of course it has a great impact in the output or the sustainability of these particular civil engineering infrastructure projects and structures respectively. Furthermore, once the level of the groundwater has been established, known, and investigated prior to the commencement and construction of our particular infrastructure project, for instance, for vertical structures, we can be sure enough that the design of our foundation or the design of our footings can suffice the level of groundwater that is present in that particular project site. And in another hand, if we are concerning with the horizontal projects, for example, the roadway or the construction of the roadway projects, once the level of groundwater has been investigated prior to the commencement of that particular civil works, we are sure enough that our output or our roadway projects are built structurally safe and stable, because we have established first the groundwater level or even the subgrade and subsurface level of water. Alright, let us also elaborate the sources of groundwater that should be taken into account prior to the construction of pavement or horizontal projects or the roadway projects. So there are many sources of water that enter the pavement subgrade. These include, first, the surface water infiltrating through porous or cracked pavements and unsealed joints, particularly through the longitudinal joint between concrete pavement and flexible asphalt shoulders. Second, the lateral seepage from saturated median ditches and irrigation ditches. Next is the shoulders and irrigated landscape features. And fourth, capillary water rising from the underlying water table. Next is the accumulated water vapor from the temperature fluctuations in other atmospheric conditions. Then poorly sealed irrigation culverts and siphons. Then plugged culverts. And last is the high groundwater table. So these particular sources are very common and are present in every project site. For example, the seepage coming from the cracked pavements and the seepage that is coming from the underlying water table and the likes. It is very important that these particular sources of groundwater should be investigated and should be known and studied, because it may affect the quality of the workmanship, and it also has a significant and a great impact in the outcome of our infrastructure projects, especially if we are concerning with the construction of roadway, pavements, or horizontal structures and projects. Let us take note that most slope failures occur during heavy rainfall periods in combination with or shortly after snowmelt. Sources of water contributing to slope instability include the seepage from irrigation ditches and pans above slopes, the interception of the groundwater table in cut sections, and rain and snow accumulation in slope scarps with subsequent infiltration and lubrication of active failure planes. For the identification of subsurface water, there is much variability in and uncertainty about subsurface conditions, but in general, most subsurface drainage problems can be identified and solutions designed prior to construction. The first step in addressing a groundwater problem is recognizing that a problem exists. Field observations are essential to early identification of potential problems. If any of the following are observed during scoping or field reviews, subsurface drainage may be required. 1 should conduct a preliminary investigation, which includes the distress or failure of existing pavement, wet spots in pavement or subgrade material piping through cracks or joints, undulating pavement surface, unlined irrigation canals on slopes uphill of the highway, cattails or wetland vegetation growing in a barrow, ditch, or on slopes, seepage from cut or natural slopes, and the evidence of slope instability such as scarps, old landslides, and trees at unusual angles. After conducting the preliminary investigation, the next procedure in order to address the particular problem brought by the groundwater, especially concerning with the highway projects and other related civil works. So the next step or the next procedure is to conduct the field investigations. The field investigations states that the validity of any analysis and design depends on the accuracy of the data used in computations. Design of subsurface drainage features requires an accurate description of the soil characteristics and a thorough geologic evaluation. Information about groundwater occurrence and soil characteristics for the design of subsurface drainage structures often requires extensive field investigation and a subsurface exploration program. So it is very important that a field investigation should be conducted prior or before the commencement of that particular civil work item, in order for us or in order for the designers to decide what particular parameters that are suitable enough in a specific type of soil properties, especially if a high level of groundwater is present in that particular project site. Soil borings and sometimes test pits are used to determine variation in subsurface conditions and water-bearing capabilities of subsurface materials. Groundwater elevations are determined at the time of boring and through subsequent monitoring. Field investigations to determine groundwater problems should be carried out during the wet season. If the concern is seepage from irrigation ditches, monitoring should be performed during the irrigation season. Various types of soil exploration and soil tests should be properly and strictly enforced to ensure that our structures, especially those vertically built structures, are structurally safe and stable so as not to jeopardize the lives of the many, especially the lives of the people. And of course, using these particular examination or soil tests, it greatly helps the designers and the planners to incorporate proper parameters or proper design tools and properties for that particular structure, especially if we are talking about the structural member of a particular building or a particular structural frame. Then, for instance, for the horizontal projects, a field density test must be conducted prior to the pouring of concrete for the surface course to ensure that the subgrade preparation and of course the sub-base course or the base course preparation are properly prepared and well compacted so as not to jeopardize the quality of the surface course or our Portland Cement Concrete Pavement or PCCP. The next point for this flag report is the analysis of groundwater problems. So there are three main points enlisted here in the presentation, and the first one is the large variability in the properties of saturated soils is responsible for large variations in flow rates and seepage velocities. And the next one is the analysis of subsurface flow requires a method for predicting flow rates and seepage velocities under different conditions. And the last one, it is important to make the best possible determination of the water-bearing and carrying properties of a formation or soil mass. This maximizes the probability of designing subsurface drainage features that perform as intended. One of the best solutions on how to control the groundwater problems are as follows. First is the subsurface drains, which are effective in controlling groundwater problems when properly designed and constructed. Many pavement and slope failures can be prevented by effective drainage of subsurface water. Underdrains are used to intercept subsurface seepage before it enters the structural material supporting the pavement and are also used to draw down the water table. The next solution is the pipe underdrains, which consist of a perforated or slatted pipe placed near the bottom of a narrow trench, backfilled with permeable backfill material. The backfill is typically wrapped in a filter fabric to prevent clogging of the drain from migration of fines into the permeable material. A French drain is an underdrain that consists of a trench backfilled with highly permeable material but without the perforated or slatted pipe. The following pictures show the subsurface drains and pipe underdrains, which considered as one of the best solutions in controlling problems related to groundwater and seepage. So the left side picture is an example of a subsurface drains, and the right side picture is an example of pipe underdrains. And of course, the French underdrain is an example of this particular pipe underdrains. The next set of pictures depict the design on how to lay out underdrain, especially on slope, and underdrain at toe of slope. So it can be seen in the diagram that the underdrain is situated below the original water table, both for the underdrain on slope and underdrain at toe of slope, respectively. And lastly, most of the components of underdrains are also integral components of other subsurface drains. Each component of a subsurface drainage system serves a particular function in ensuring that the drain performs as intended. Design of any subsurface drain should result in a system that is cost-effective, constructible, compatible with the surrounding soils, and that will provide adequate drainage throughout its design life. The following are basic components of a subsurface drainage system. First, filter or separator layer. Next, the conducting drainage layer. Third is the collector pipe, then outlet, and the appurtenances. Thank you so much, guys, and that ends my presentation on groundwater and seepage according to variability. Thank you so much, and the following are the references in crafting this vlog report. First is the online link or the online journal coming from the internet, and of course the Handbook of Engineering Hydrology edited by Said Islamian. More power, and to God be all the glory. Thank you so much.